That's fine. So we're going to spend about 25 minutes doing this lesson. Normally this lesson is an hour 15. So what I'm going to do is I'm going to put up the slides and not actually say anything about these slides. So this session is on a guide to good experimental design. It's a talk that I've given to many audiences. I've done it with families at the AAAS American Academy for the Advancement of Science Family Day. I've done it with DOE Science Bowl. I've given it as a Saturday presentation for Engineering for Everyone. And I do this with the camps and also in a class that I teach. So I'm an experimentalist, and I need to do good experiments in my line of work. If I do an experiment that doesn't have proper design, I can't draw proper conclusions from the work that I do. And so all the work that I do is wasted if I don't do a good design. So this talk, it has two parts. The first part talks about, well, what is the difference between a design or an experiment and an observation? And then the second part is the one that has the activity, and that's what I'm going to jump into. So the picture is we have an engineer, and the engineer has under their capability certain knobs that they can adjust. And so the second half, which is what we're going to be talking about, is how do I figure out which variables are important? So I have 8 different knobs, and there's this funny joke that exists that says, well, why do engineers get paid so much? It's because they know which knob to turn. They know how much to turn it, turn this knob by 30 degrees, and everything is solved. So the goal of this is to understand which knob to turn. So I'm going to skip. Oh, OK. Yeah, so I'm going to skip all of this. All of this material at the very beginning. I actually have a recorded lecture on this part. All this stuff at the very beginning is just talking about definitions. So the definitions that you'll see in an AP statistics course. So all this stuff, just definitions, and talking about census versus sampling, placebo effect, lurking variables, confounding, good design. This is the most important slide from the first half, so I'm going to spend time talking about this. In a good experimental design, you're going to have 3 key principles. The first principle is you're going to control the effects of lurking variables by comparing 2 or more groups. So you need to be able to say, these 2 groups, after I've done my treatment or after I've varied my factor, there's a difference, and the difference is because of the factor, because everything else was the same about them before. The goal is to be able to get rid of the effects of lurking variables. So lurking variables are things that the researcher is unaware of that may explain the relationship between output and input. So the goal with this good experimental design is control that effect by doing a comparison. So groups are identical in every single way, and you look for differences in the groups after you've done the treatment. The second key principle is randomize. So you want to randomize the assignment of people or of units or of things that you're going to test to the treatments to reduce the effect of lurking variables. So a good experiment will have a control group, and I will randomly assign people to the control group and randomly assign people to the treatment group. I don't want to, for example, put all the women in the control group and all the men in the treatment group, because now I've confused the effect of gender with the effect that I'm trying to study, which might be some treatment. So I want to randomly assign people to the different groups so that I can eliminate these sorts of lurking variables. The third key principle is to replicate each treatment. And the reason that you want to replicate is because there's always going to be random noise. There's going to be chance variations. There are going to be things that are beyond your understanding or your ability to control for. But if you repeat the experiments many times, it'll be evidence that one thing has an influence on another. So a common example, people hear 3 out of 4 dentists prefer brand A versus brand B. Does that sound convincing? Not really, because one person changing their mind, all of a sudden it's a 50-50 split. But if you had 3,000 people preferring one brand to another, then you're going to say, there's evidence that this brand is actually a better product. So the key principles, anytime you have an experimental design, it's going to satisfy these 3 key principles. There's going to be control, there's going to be randomization, and there's going to be replication. OK, so there's an activity that I do which basically analyzes some designs. I'm going to briefly explain 2 or 3 of these, and then we're going to get into the activity. So imagine that we randomly assign people to 2 different groups. Group 1 we give a treatment to, Group 2 we give a placebo to, placebo being a fake or sugar pill, and we make an observation in both groups after.
Is that what those notations mean? Because I had found
Yeah.
what the TX was, but I didn't know what the 2 dashes were.
Yeah, somewhere in, oh, here, yeah. So TX means the treatment is made, which means that we're varying the independent variable. So the thing that's under our control, the X variable, we're adjusting it. Double dash means that we're doing nothing in that time slot, so we're doing a placebo or we're doing nothing. And OBS means that we're making an observation, which means that we're measuring the Y variable. We're measuring the response variable. So treatment, we're controlling the X variable. OBS, we're measuring the Y variable or the response. So in this picture, we randomly assigned to 2 groups. First group gets treatment, second group gets placebo. So the example that I give in the first set of slides, it talks about having this fictitious product that we've developed, hair grow formula, and your boss wants you to evaluate whether this thing actually works. So you're going to test this out on people. You're going to give some people the hair grow formula, which is the treatment. Some people are going to get the placebo, which is plain shampoo. And you want to see, is there a difference in month 13 for the treatment group compared to the placebo group? So this experimental design is good because we have control by comparison. We're going to compare these 2 results. We have random assignment to people to different groups, and we have replication because there are many people in each group. So this is a good experimental design. The question is, well, what does it tell us if we observe a difference? Well, if we observe a difference, then this experiment can show evidence that the treatment causes the difference. We can never show proof. So this is a very important point. You never get proof in an experiment. It's one of those things like people say, I've proved that da 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 da. You never get proof. You only have overwhelming or super convincing evidence that one thing causes another. Okay, so this is a good experimental design. This design, what about it? We have group 1, we give them the treatment, we make an observation. I don't have control. I don't have random assignment. This is actually an observation. This is not an experiment. And as parents, a lot of us are parents, we're very famous for this experiment. So how many people tell their kids, you have a cold today because you were standing outside in the rain yesterday? All guilty of that, right? So observation, you have a cold. Treatment, you stood outside in the rain. So then you think standing outside in the rain causes you to catch a cold. So that's not an experiment. The experiment would be you tell your other kid, yeah, you stay inside, you send one kid outside to stand in the rain, and then you measure whether they catch a cold or not. All right, not an ethical experiment, but that would be the proper way to control. And you have to randomly assign which kid gets to stand outside in the rain. All right, so this shows nothing other than the observation occurs after the treatment. Okay, I'm going to skip this. There's an observation before, and basically this is going to tell us that there's a difference in the response. So there's a change in the response between before and after. This is the one that I want to focus on. This is the one that we're going to do the activity on and the key to it. So there may be 2 different treatments. So one thing could be the shampoo versus hair growth formula. A second thing could be change in diet. So diet is also responsible for hair loss. So second treatment could be I'm going to eat more vegetables. I don't know, something like that. So group 1 gets assigned hair growth formula and eating vegetables. Group 2 gets hair growth formula, keeps their old bad diet. Group 3 eats vegetables, gets plain shampoo. Group 4, plain shampoo and bad diet. And we're going to observe the 4 groups and we're going to compare. So this is a good design because I have control by comparison, I have random assignment, and I have replication. What does this comparison show? So I have 4 different groups. I'm going to pick 2 at a time to compare. So there are 4 choose 2 different ways to compare. So you have to go back to your number theory. 4 choose 2 means 4 factorial divided by 2 factorial times 4 minus 2 factorial. So that's going to work out to be 6. So there are 6 different comparisons I can make. So if I compare group 1 and 2, I can tell whether both treatments together is better than just hair growth formula. I can compare 1 and 3, both together better than change in diet. 1 and 4, both together better than nothing at all. 2 and 4, hair growth formula by itself compared to nothing. 3 and 4, vegetables versus nothing. And then I can compare 2 and 3, hair growth formula versus just vegetables. So there are 6 possible comparisons, and basically what you're trying to see is, individually, do these factors cause a response? Is the response better if I combine these two things together versus if I do them by themselves? Okay, so we're going to jump into the activity, screening design. So the screening design, it's a type of experiment where you're trying to figure out, well, which knob do I turn? So there's a systematic way to do that. I'm going to skip this. Basically, the idea is, well, I'll talk about briefly. Basically, in nature or in process, there's things that you can control, things that you can't control. And then there's these outputs. And the goal of engineering, or at least in the screening design, is which one of these inputs can I adjust such that I get the output that I want. Skip that, skip that, skip that, skip that, skip that. OK, so getting to this slide. So looking at the way that we represent these designs, we can represent them graphically. So this table, which had these 4 different groups, what I can look at is there's factor 1 and there's factor 2. And I can represent factor 1 on the horizontal axis. I can represent factor 2 on the vertical axis. So this point here has factor 1 on, meaning that I have treatment 1, and it has factor 2 on, meaning that I have treatment 2 on. So this point in the upper quadrant, in the first quadrant, has both factors on. This point has treatment 1, but it has negative for x2, meaning that treatment is off. So I have only treatment 1. This point, number 3, has treatment number 2 on and treatment number 1 off. So that's this one. And this one has both of them off. So I can represent this complicated table by just these 4 points in 2-dimensional space. OK, so what we want to do is this LED activity. So I'll ask the lab assistants for some help. So clear your space, because you're going to need to work a little bit. And what we'll do is, this group is really small, so we need 1 bag per person. Normally, with the activity, you typically will have 2 bags per, or sorry, you'll have 1 bag for every 2 people. So you'll have teams of 2 usually. But for this, we need to have enough experiments going on at the same time, so everyone needs their own bag. So each team, you're going to be individually a team. Each team has a bag. Inside the bag is a battery clip, batteries, an LED, and a resistor. And I can take one of the bags so I can demonstrate. Oh, we have exact. All right. No, I have some extra ones in here. Yeah, I forgot I have an instructor's bag. OK. OK, so you have the resistor, which is a wire and a tiny blob attached to it. You have an alligator clip. You have a battery clip. You have batteries. And there should be a light-emitting diode. Now, normally, this particular topic is done before we introduce the breadboards. And the reason that we do this before we introduce the breadboards is that it allows students to appreciate what the breadboards do for them. Basically, allows them to hold things in place. So we're going to have you do it the way that it probably will occur in the STEM clubs, which is before you introduce the breadboards. So you're going to be building stuff, holding it in the air. So it's going to be easier to see, but it's going to be harder to check. So what we want to do is we want to carry out a 2-factor experiment to determine under what condition will I get the LED to light up. So the 2 factors that I can do, so I don't want to talk to other teams because we want independent results. The 2 factors that I can do is I can take the resistor and the LED and put them in parallel or in series. I'll explain on the next slide what that means. The second factor is if you look at the LED carefully, one of the legs is longer than the other. So we want to figure out, should the red wire of the battery clip connect to the shorter leg or to the longer leg of the LED? OK, so I'll walk everyone through this because we're a little bit limited on time. So the first factor is the resistor and LED in parallel or in series. In parallel, what you have is you have the resistor 2 ends clipped on one side, or the resistor and the LED clipped on one side, and resistor and LED clipped on the other side. in your kits, the students will not get the clips. The clips are actually pretty expensive. They're like $2 a piece. So what you'll get is you're going to get the battery clip without these probes. So the probes are the expensive part.
Right.
The probes are the $2 a piece thing. And we had to hand solder these. Okay, so go ahead and load your battery into the battery clip. And keep in mind that the flat end of the battery goes on the springy side of the clip. And what we will do is we'll do this first configuration. So you don't need the separate alligator clip. So put this one aside for now. You only need the battery clip, the resistor, and the LED. So we're doing this first configuration. So we want parallel, and we want the red to connect to the shorter leg. So we're going to clip the red, and the way that these particular ones work, you push up and it exposes a clip. So you're going to clip the red to the short leg of the LED. And you can bend these legs and so forth so that they're convenient to clip. Don't worry if your LED breaks. Typically, every session I lose at least one LED, valued at 7 cents a piece. All right. And then, oh, I clipped it wrong. Oops. OK, sorry. I clip the resistor and the short leg of the LED. So I need to clip both of them. So, question? So you have short leg, and then this also needs to be clipped. So these two together, clipped together. Yeah, so you're clipping both the resistor and the LED onto the short leg with the red clip. And then you clip the long leg to the black and to the resistor together. And you see, does it light up? And in your notes, you'd write down, yes, it lights up, or no, it does not. So maybe the lab assistants can circle around and answer questions as we're going. OK, so you record, does it light up, does it not light up?
That's before you put the resistor on.
Yeah. So it helps to, yeah, you can twist the wires to hold them in place better. Say it again? Yeah, in one of the bags. And then the bag you take it out of, set it aside so I know to replenish the resistor. OK, so Lamon's still working on this one. Yeah, a little bit of dexterity. So Winter, go ahead and help Lamon with this one. So I'm going to continue on if people are OK with that. OK, so has everyone tried clipping the red to the short leg? So now we want to clip the red to the long leg. So the suggestion is unclip the red, unclip the black, move the black to where the red was, move the red to where the black was. But don't have it at the same time, red and black on the same spot. You're going to short the battery, and it's going to burn up. And see whether it lights up. Switch red and black. Unclip one at a time and try to hold it.
There's different colors too. Well, you already did it. Yeah.
Is that the way it's purchased? Or?
We'll talk about it in a bit. OK, so you've tried parallel short leg and parallel long leg, correct? Is everyone good on that? All right, so record whether it's lighted up or not. All right, next step. Has everyone tried So I noticed teams are talking to each other. So part of this is it's supposed to be independent results. All right, so some people are working parallel, that's fine. Okay, so everyone has tried parallel short and parallel long. Now we want to do series. So for series, it helps to use the alligator clip that's by itself. So for series, let's say that we clip, let's say we're doing this one. So we're going to clip the long leg of the LED to the resistor. And the resistor, it doesn't matter which side you clip to. It's the same. The LED is different depending on the sides. So I've clipped it in the middle to connect the LED to the resistor. And now I'm going to clip the red to the short leg of the LED and the black to the resistor and see, does it light up? So we're doing this box. So we're doing the red to the short leg, the black to the resistor. You did all of them? Okay. It's a result. Yeah, in the textbook, it has these pictures, so they can follow along with those two. Say it again? I don't know. What is it? 35. Yeah. Yeah, it's in the book in page 35. Did you get a book? Did I give you a book? I didn't give you a book yet. Oh, you got one? Okay. Okay, so once you've gotten that one, swap and do black to the long leg, or black to the short leg rather, and red to the long leg, and see whether it lights up. That's this condition. Yeah, oh, sorry. So this one would be, so we just switched the red and the black. So red to the resistor, black to the other leg. So normally this session probably would take 35, 40 minutes so that students are comfortable and they're not rushed. But I'm going to press on so that you guys can see I'm going to press on so that the group can see sort of what comes next. All right, so let's share some of the results so far. How many groups got theirs to work, or how many individuals got theirs to light up? So we have Stephanie, Nancy, anyone else? Did anyone get theirs to light up at all?
Oh, yeah.
Okay, so there are a couple of people that got theirs to light up. Anyone get theirs at any instance? Did anyone get theirs not to light up? Okay, so there are a couple. All right, so this is one of the things that allows students to experience a curiosity gap. So I intentionally made it so that some of them work and some of them don't work. Ah.
Without saying, I'm like, I know this is supposed to work.
All right, so.
He just said he made some of them work intentionally.
Okay, so let's summarize these results. So let's look at these different cases. Did anyone have this one work?
No.
No. Did anyone have this one work? Yes. So this one works some groups. So some groups this one works, some groups it fails. Anyone get this one to work? No. This one to work? No. So this is the only configuration that works. It only works some of the time. And so when you're designing an experiment, when you have variation at a given setting, that's usually an indication that there's a lurking variable. So I put lurking variables into this experiment to be able to stimulate students to think about, well, what factors were overlooked in this experimental design? So at this point, you'll talk to each other. So the groups that got theirs to work, talk to the groups that did not get theirs to work, figure out what's different about the different bags. So go ahead and talk and figure out what's different. Talk to. None of yours worked? Okay.
Mine didn't work either.
Yours didn't work? Nancy's ones worked, right?
Yeah, but she don't even want to share.
You're not sure?
She would not share. I'm like, let me go. I mean, how you just not going to share the doggone lid?
No light. You talk to the other teams. Still doesn't work.
Well, I have two batteries.
Oh, it did work.
You have one.
No, I thought I had it all figured out what it was doing. Just when I thought it was all figured out.
I didn't even notice that.
Still both got one.
Yeah. You
know,
got
we did
two
look
batteries.
Did we look at the strikes?
So much power.
Well, what we didn't
I just can't do it. I haven't got the power.
So I understand that parallel
When we
doesn't
insert
work
those
because
Parallel should work. So
because the
series
current
should not
probably
work.
going through
Yeah,
the
the resistor.
But resist still doesn't work, and I don't
Right,
know.
that one's series.
Yeah, but
So
why is it not work? Shouldn't it
so in the
even light up?
different
You know what, could it be also battery?
we'll talk about that. Yeah. Oh, go ahead.
Did you give me a battery that doesn't work either?
No, the batteries are all good.
Because I changed them and it still won't light up.
Okay, so let's. All right, so some people have figured it out. So let's.
No, the back. Look at this. They have more. She got more voltage going through.
All right, so let's discuss it. Let's bring it back. So, all right, so the students are going to go through the same emotions that you're going through, like I can't believe this happened, and da-da-da. Is it this? Is it that? And you want to encourage that. You want to encourage them to be curious. You want to encourage them to think critically as to what works and what doesn't work. This is also a useful skill for debugging. You need to be able to debug and figure out what's wrong. All right, so some of the things that people pointed out. So what was it?
One of us, I have like, you didn't say how many, it says a AAA battery.
A AA battery.
A double A. She has two of them.
Yeah, so some groups have 2 AAs. Some groups have 1 AA. There's one other difference between the different groups. So 2 AA versus 1 AA. And I will say that every group's LED works.
Here, try this. Put this one on yours.
So in the interest of time, I'm going to spoil the second surprise. I think Stephanie. Okay. Yeah. Don't spoil the surprise. All right. Well, Stephanie figured it out already. So what was the other difference?
There's a difference in the stripes and the resistor.
Oh, no. She figured it out earlier in the session when she was talking with Donnell. The color. So some of the LEDs are red and some of them are blue. Blue. And I intentionally picked. Yours is red. Yeah. So the reason that they're all clear, I don't want to tip the hand that they're different LEDs, but there's some that are red, there's some that are blue. So now let's summarize this experiment so that we can understand this hidden variable. Okay.
Not a culturally,
Not culturally responsive.
culturally responsive teacher.
You got to fail sometimes. So getting used to the idea that not everything's going to work the first time and be able to figure out what to fix is an important skill. So there's a second experiment that can be done, but you've actually already done it. So there are two other working variables, whether it's one AA or two AAs, and whether you have a red LED or a blue LED. So based on the results so far, how many people had two AA and red? Did it work? Okay, so two AA red works. Two AA blue, that works. Two AA blue? It's supposed to work. All right, so Stephanie's doing it, let's see. Yeah, so two AAs and blue is supposed to work. Anyone have one AA and red? Okay, that was supposed to work. Now with one AA and red, you have to look at it very, very carefully. So do the look at it end on. Yeah, if you look at the red LED end on, you can see a tiny bit of lighting. So this one does work. But the groups, yeah, if you have it connected correctly and you look at it correctly, it does work. The one AA blue is the one that fails. Okay? No matter what you do.
So it should work. He said one AA red should work.
One AA with red, if you look head on, it should work.
Let's see.
Like, yeah.
Here, I got my battery in mine.
You can just put it.
No, she got it. What's that I got?
Oh, so
No, let's see. Yep, put one in here.
Yeah, the other thing you can do if you're just testing, skip the resistor if you're just testing.
I see it right here, like in my hand. As far as in our kid,
Nothing.
Yeah, so you have to look directly head on. Oops, I knocked yours off. All right, so this is the long line, right? So clip that side. Clip that side.
well, let me see.
Oh, so it's not as bright.
Yeah, and you have to look directly at that end. No? Let me see your one.
I'm about to say now, unless you seeing something Stevie Wonder, I'm
All right, AA battery clip.
You gave me the dud battery. I'm the real. No, I'm not that. Not over here. It's some trouble over here.
All right, there's something wrong with yours. All right, I got it. There really is something wrong. Let me swap.
There's something wrong with mine.
Let me swap batteries. I got to pull the dead battery out of circulation. All right. Dead LED maybe.
Yeah.
All right. Or are you sure yours is red?
It worked with hers.
Is it red or is it blue?
Red, and it worked with hers.
All right. I got to explore this a little bit more.
See, I got to experiment inside of an experiment.
All right. So let's bring it back. There's a few things I want to talk about before we end this activity. All right. So bringing it back. So the key conclusions of this experiment. The first, we're going to have a mnemonic. So the red must be connected to the longer lead of the LED. The LED is our pal. So positive connects to the anode. The anode is the longer leg of the LED. So LED is our pal. Positive goes to the anode, goes to the longer leg. In order for this to light up, the resistor and the LED have to be in parallel. The resistor serves to block current flow. So because they're in parallel, the current goes around the resistor mostly and just goes through the LED and lights it up. When you put it in series, the current tries to go through the resistor. It's too much of a voltage drop across the resistor to light up the LED. So the resistor I gave is a very large resistance. It's like a mega ohm. I forgot exactly. Is it 1 or 10? Something like that. The LED actually may still be lighting up, but it's so dim that you can't perceive it. But if you measured it, you can probably detect some light. So even in series, it probably still is on. Now, in practice, and this is an important point, so this activity, it's to teach design of experiment. It doesn't teach good circuit practices. When you work with LEDs, you want to always have a resistor in series with the LED. And the reason is the LED is a current-controlled device, meaning that if I try to apply a voltage, like I apply 5 volts across an LED, I'm going to burn that out because the current that flows to the LED will be really high. I need a resistor to limit the amount of current that goes through it. So in practice, you want to have a resistor in series, but you want to have a small resistance. You want to have something like 200 ohms so that you safely limit the current to about 10 or 20 milliamps. So in practice, you want it in series. In this example, it has to be in parallel because the resistance is so large. Okay, the red LED will light up with either 1 or 2 AA's, but the blue LED needs 2 AA's. And the reason is that the energy of the photon associated with red light corresponds to 1.9 electron volts. And so a 1.5 battery, well, it's less than 1.9, it can still turn it on. So there's enough energy that it can just barely turn it on. If I got up to 2 volts, it'll suddenly be very bright. The blue LED, however, the energy for a blue photon is 2.9 eV. It's so far away from 1.5 that there's no hope of it turning on. The red will turn on even though the voltage is slightly less than the actual energy. And the reason is that there's thermal energy, and that thermal energy is enough that there's a few carriers in the conduction band that can recombine and produce the red light. And the other conclusion of this is that if you do small experiments in series, so you do some things, see what happens, and then do some more experiments, it can save you a lot of time. So rather than trying to study all 4 factors at once, we'd have to do 2 to the 4 or 16 experiments. We did 4 experiments, and then we repeated, and actually we reused the results from those 4 experiments. So we can actually do the experiments and figure things out in fewer trials than if we put everything together, because we're not wasting time doing experiments that won't work. So these are the key conclusions for this activity. The session continues with additional topics. These additional topics are more advanced. They're in the book. They explain a little bit of it. I'm going to end here. It's 3:46. So what we'll do, disconnect your batteries from the battery clip, put everything back in the bag. The one that didn't work, I'm going to set yours aside to figure out what's, that one at all?
Mine didn't work at all.
Yours didn't work at all. So we need to set yours aside, figure out what happened to your clip or to your.
You're going to put like a big.
Okay, so how many of each part do you get? So I believe for this activity, you get 10 of the battery clips. You have enough batteries, so you get like 5 of the AA1 and 5 of the AA2. You actually have more than that because some of the stuff gets distributed to the students, but you have enough to probably run, if you're working in groups, with a group size of about 20.
That means you got 10 double.
I think it's something, I have to look at it again. I think it's something like 5 of the 2 and 5 of the 1, okay. So that would be 10 groups. Okay. And the groups can be 2 people or it could be 3 people, so 20 to 30 people. It's possible to also borrow parts from other activities.
That's how you know it's mine.
Doesn't work.
I'm going to put all the parts
all right, all right. Okay, so that, yeah, so put yours in his as well. Put all those together. Yeah, put your bag in there as well. I have like 40 or 50 of these bags that I go through, and every session something breaks, so it's not unusual.